So we're going to start the next topic, which will be a continuation of the activator pattern that we started talking about last time. Now we're going to talk more about the implementation aspects of the activator. And then we're going to spend some time talking about some other patterns that we've been discussing as we've been covering the various bound services, proxy and broker. So first, let's talk about the second half of activators. So what we're going to do here is we're going to talk about how the activator pattern can be applied in the context of Android, or how Android applies the activator pattern. As you may have remembered from our last discussion, the activator pattern participants and the structure maps very, very nicely onto Android capabilities. And as we start talking about the implementation steps in the activator pattern, once again, it's remarkable how many of these things map kind of one-to-one onto what Android does. It's also kind of fun, if you take a look at the pattern description, you'll see that there's a number of different design alternatives that are described in the implementation section. And as we go through the implementation part here, I'll illustrate both the generality of the implementation approaches as well as describe how Android addresses those particular implementation choices in the things it does that pertain to activators. So the first thing to note that you do when you implement the pattern is you figure out what the services are and how do you identify them. And you also figure out what the service identifiers are, which are the ways you actually identify the services. So, of course, the idea is to encapsulate units of self-contained application behavior in the context of something called a service. That's the generic concept that's important. In Android, this is really easy because services are things that inherit from the service base class or from the intent service class. So services are real easy to figure out in Android. There's a one-to-one mapping between the concepts and the pattern and some realization of those concepts in the context of Android. And if you take a look at this link or this path name, you can find the code for services in Android, which is kind of fun to look at. The only real method that you have to implement is the onBind method, which is done for you by the intent service, but otherwise you have to fill it in to return null. And that's a way for it to tell the difference between different kinds of services. There's also the question of service identifiers. Now, in conventional networked applications that use the activator pattern, and we'll talk about a bunch of those later, typically you identify services via some kind of identifier scheme, like a universal resource identifier or a universal resource locator, or an interoperable object reference, or a TCP/IP host name or host address and a port number. Those are classic ways of identifying services in those environments. In the context of Android, of course, we identify services via intents. And there's a couple of different elements in an intent that are used by the intents framework in order to be able to figure out which services are being referenced when we go ahead and do a start service or a bind service. And some of those elements include things like what's the name, which is optional. You don't have to give it a name. You can leave it up to the Android intents framework to figure out what service matches based on other things besides the name. If you use the name, then it's basically an explicit intent. It's explicitly naming, says this thing goes with that particular entity. There's also other things like the action. What's the action that's being used? So is it some kind of action that relates to, viewing something or editing something, for example? Or, is it a URL action? You're going to download something. There's also the data that goes along with the action. This would be things like a URL or some other URI or path name that identifies either a local or a remote piece of content. So that's another thing that can go into an intent to help identify which service is responsible for processing the intent. Yet another thing that can go into an intent is something called the category. For example, there's a category for launchers, which are things that get up on the basic application launch screen. There's other kinds of categories of applications as well. So these are the kinds of things that are actually used by the underlying Android system and the activator framework, the Activity Manager service, which is the activator part of Android, in order to figure out who gets launched, what service to run when something gets sent out. You also then have to decide which services do you want to activate and deactivate on demand. And not every service that you might have in your system is worthy of being activated and deactivated on demand. So you have to kind of figure out a couple of things. You have to figure out things like what's the overhead for being able to activate something on demand or not. what's the downside to keeping something running for a long time? There are also, I think I should mention this too, there are also security implications. So some services are really important, and you want to make sure that they're always there. You don't want people being able to dynamically change them. For example, I don't think it's the case that you can dynamically activate the radio portion of Android, the part that does the actual phone management. That's the sort of turned on by default, and you don't activate and deactivate that. You can imagine that would cause all kinds of problems with probably missed calls because things would take too long to launch. So you have to figure out what it is that you want to be able to run dynamically and control dynamically. Some of the services we've seen on Android that do this, things like email, media playback services, services for sending and receiving various kinds of messages, short messages, multimedia messages, alert services that going to pop up when calendar timers expire and elapse, and you have to alert someone that something is about to happen so they can go make a call or join a meeting or something like that. So those are some of the services that the Android developers have deemed relevant to start and stop in a dynamic way. If you take a look at packages, the packages apps directory, you'll find lots more examples of bound and started services there. And there's a bunch in Android as well in the frameworks part. The next thing you need to do is figure out what the service activation and deactivation strategies ought to be. And one of the key considerations there is what is the context in which a service gets executed, gets run. And there's a bunch of different choices. If you're programming in lower level operating system environments, things like the Linux inetd or Unix Internet daemon, inetd, that we talked about briefly last time, the super server model. In that particular case, you're probably going to have a process be the unit of activation. That's the service execution context. You're going to launch a process when something happens. In other environments, like if you're running in some kind of embedded system that doesn't have processes, you might spawn a thread. If you're running in the context of something like Android, if you think about what's being launched here, which is basically a service, that's really not a process or a thread. It's really more of a middleware-centric container of sorts. So it's an abstraction that it hosts some application logic. Naturally, it can run in a process or not, or it could run in a thread or not, but it's basically a somewhat higher level abstraction. So you have to decide what the right level of granularity is. Obviously, Android does it as a middleware container. You also have to figure out how the service is going to register itself with the activation framework. Is it going to do it dynamically by some kind of API call like register service? Is it going to do it more statically by defining various things in a manifest file so that when things get started, the system knows which place to launch and how to dynamically load the various resources in and so on? Those are decisions. Android typically goes with a static text file approach with a manifest file. You also have to decide whether the activation framework is going to be responsible for initializing the service or not. And there's a couple of different cases here. If a service doesn't require any initialization, if it just starts, then obviously the framework doesn't have a whole lot of work to do. If the service requires certain state, then it's up to the developer of the activation framework as to whether the activation framework is responsible for initializing the state, or whether the service that gets started is responsible for initializing its own state. In Android, anything that's important gets done by the service. It's not really done on a service basis by the underlying middleware. There's also another set of considerations about how do we deactivate services. So activating services is just half the battle. In the Activator model, once you activate something, you have to figure out how to shut it down. Of course, you could keep it running for an indefinite period of time, but to some extent that would defeat the purpose of an activator, because you really want to reserve or preserve resources or conserve resources by shutting things down when they're not being used. And there's a couple of different techniques you can use here. You can have the service trigger the deactivation. The service can say, I'm done, I'll shut myself down. That's kind of the way that intent services work. You can have the client trigger things. Some client can say, service, stop yourself. That's another model. And then you can also have things where the activator decides to shut stuff down. And that could be based on a variety of different things. Android supports all of these different models in various degrees, right? So with started services, when the service starts to run, it'll run indefinitely, and it has to stop itself by saying stop self. Or So that's the service-triggered deactivation model. Or another component could say, service, I want you to stop yourself. So that's a client-triggered approach. And of course, the Android runtime system might start to notice that memory is getting low, and it may say, hey, you got to shut yourself down. So that's kind of the activator-triggered model. With bound services, typically the way things work is that multiple clients can connect to the service, and as long as some of them or one of them is available and has a binding open to that service, the service will remain in memory. And we'll see some interesting sort of hybrid approaches in a minute when I show you some of the implementation code that appears in Android, how they deal with some of these issues. It's kind of cool. So you can take a look at the website. There's a link here that gives you more information about service lifecycle. But be aware that Android gives you all the tools to do the different kinds of deactivation strategies, and it's up to you to figure out what to do. The key thing you typically don't want to do is not let the service run indefinitely if nobody's using it, because that would be overly consumptive of resources. Some other things you need to do: figure out how you're going to interoperate between the activator and the service execution context and the service itself. So how do these things interact with each other? The key thing here is the interaction between the service execution context, which is typically either a process or a piece of middleware container, and the service, which is the thing that's doing the business logic that's defined by the end programmers. So there's a couple of different alternatives here. One thing that you typically have to do is come up with some way for there to be callbacks, either from the execution context to the service or from the service back to the execution context to do various kinds of things. Android supports both of these means, of course. The most obvious set of ways these interact is with the lifecycle callback hooks that are dispatched automatically by the Android runtime framework when a service starts, to call on create, when intent shows up via onStart command, when you do the various bind service calls, which trigger the onBind method, and so on. So there's a bunch of callback hooks that you can define, and those are interactions between the Android container infrastructure and your service and your hooks. And of course, your service can also make callbacks into the Android container infrastructure to ask it for various things as well. But that interaction is something that's very stylized and important to understand. Then you also have to figure out how to implement the activator, actually do the activation. And in Android, this is done by something called the Activity Manager service, which you can take a look at. It's a very, very complicated piece of code, very large. And it handles activation for lots of things: activities, services, broadcast receivers, and so on and so forth. It plays multiple roles. Even though it's got the name Activity Manager service, it manages other things besides activities. There's a couple of issues to consider here. When you design the activator, do you want to have a singleton activator or a shared activator that's used by all the services running in an infrastructure in an environment? Do you want to have one that's exclusive on a per service basis? Do you want to have some kind of distributed activator where you may have some centralized node that's keeping track of who gets to run and where they run, and so on? And again, there's no one size fits all or one right solution to all these different design considerations. The trick is to figure out what the alternatives are and then make the choices that make sense for you. In Android, they have essentially a singleton or shared activator. The Activity Manager service is the guy that is the role, the component in Android, the service, the super service that activates other things. Another consideration here is, what is the degree of transparency with respect to activation? Is this something where the application client has to make a special call to get a service started, and then it does other requests? That's what's called explicit activation. Or is it something where you just make a method call and the underlying activation framework activates the service implicitly and without you having to think about it directly and do something special? So the way it works in Android, which is different from other pieces of middleware, by the way, is you have to do explicit activation. You have to say start service or bind service, and then that triggers the service to be started, and then once that happens, then you can send messages back and forth. Now, you can also, to some extent, kind of do a little hybrid thing where you can pass in an intent or extras with the intent that goes along with the original service. So there are a few kind of things that straddle the line between implicit and explicit. But in technologies like Corba, we'll see later that there's much more support for implicit activation. You just make a method call, and boom, something magic happens under the hood to get the job done. So what I'd like to do now is take a tour through a piece of an interesting service in Android that demonstrates the use of Activator. And I'm just going to look at a part of it now. Later, when we talk about the broker pattern, we're going to come back and look at the full-blown glory of this stuff, because it's really cool and it's got lots of interesting interactions. This implementation, by the way, actually has a lot in common with the download file stuff you're doing that's the asynchronous version, because it relies on passing in asynchronous callback objects using one-way methods that will not block the caller while things are taking place. What this thing is, it's a network settings activity, and you can use it, if your phone supports it, in order to be able to find out what carrier networks are available. You know, so like you don't often see this too much when you're in the US. Usually you're with a single provider. You know, your phone just starts up and it's running with Sprint, or it's running with AT&T or Verizon. When you go overseas, however, oftentimes you're roaming, and there will be a range of different network providers to choose from. And so this particular network settings app or activity allows you to be able to see the networks that are available, and then you can conceivably choose one that you want to use. So here's basically the way this works, and by the way, all the source code is available. You can take a look at that if you're interested. So they have this network settings activity, and it has an onCreate method, and so when you launch this thing, it turns around and it makes a call to start service. And it invokes start service to go ahead and launch the network query service. But it doesn't talk to that directly, of course. It talks to the activity manager service. And the activity manager service takes the request and all the other things, and then it goes ahead and it launches the process to run the network query service if it's not already running. So that's really the Activator part right there. So it's activating it on demand. And then what happens is there's an opportunity that the service gets to initialize itself via its onCreate hook method, its lifecycle hook method, and it goes ahead and does what it needs to do. And then what's interesting, and we're not going to look at this in any detail right now, but we'll come back and look at this later when we talk about the broker. The next thing that the activity does after it calls start service is it turns around and it calls bind service. So this is kind of an unusual model. It calls start service followed by bind service, which looks a little weird, right? So far we've only looked at services that called start service, which are started services, or services that called bind service, which are bound services. But this is an example of something that does both. And if you read the comments in the code, it basically says it does this so that when we call start service, the service will remain running indefinitely. So we want this service up and running all the time. And then we call bind service, so we get back a binder object, and we can interact with the service by using asynchronous binder communication via one-way AIDL calls. And we'll look at that in a little bit more detail later. But I thought that was kind of an interesting example of using start service to explicitly activate something that will remain around, and then use bind service immediately after that in order to get back a proxy that the client can use to invoke methods on the service. So it's sort of a hybrid approach. But the key point there is that it has the examples of the Activator. It launches a service on demand. Any questions about that? So again, if you're curious, take a look at the source code. It's got a whole bunch of really cool things going on there. It registers a handler with the underlying radio interface layer, which is the part that actually keeps track of the service, the carriers, and the network availability. And when things change, there are callbacks that get made in the service. It's really cool. So we'll look at that later. Okay, so to go ahead and summarize this particular discussion, Android started and bound services use the Activator pattern. And as you can see here, they use the stuff that pretty much straight out of the book. Looks just like what you'd see there. These services can be run in different execution contexts. Most typically, if you don't do anything to the contrary, they end up running in the same process as the caller, which is typically an activity. But without too much effort, you can tweak the Android manifest file to say, I want this thing to run in a separate process, so it can then be launched in a separate execution context than the context that was originally calling it. And if you want to be able to do threads and have the service run in a thread, then you can program that by inheriting from intent service or doing something else not unlike what you guys have done for your programming assignments to implement multi-threading on the service side. Okay, so that's basically Activator. To recap, what we talked about last time. Activator is a pattern that makes it possible to launch things on demand. And we talked about sort of the pros and cons of that. Then we just saw some examples in Android where it gets used in order to work with launching bound or started services to do various behavior processing on behalf of the client applications. Okay, so in the grand scheme of things, what I just talked about probably should have gone about a month earlier in the course, because when we first started talking about services, we could have talked about activators, because they're a concept that's very fundamental. What we're going to talk about now is something that makes a lot more sense once we've gotten to the point where we're discussing AIDL and binder RPC, because it's something that really figures prominently in that context. So what we're going to talk about here is we're going to start talking about the proxy pattern. And as we'll see, the proxy pattern is a pattern that appeared in a couple of different places. It appeared in the Gang of Four book, where it's focusing primarily on a very simplistic way of doing proxies. And then later, we'll see it appeared in the POSA 1 book, where it was described a bit more generally, focusing on communication that occurs in environments where you're going across address spaces. So we're going to kind of merge these two things together, and we'll talk first about the pattern, and then we'll talk about how the pattern gets applied in the context of Android. So what's the context? Well, the context is, in most environments where you have to cross address spaces, it's not really feasible to access the internal details of an object directly. If it's in a server process, you just can't get to it from the client. You're separated from an abstraction boundary that could be a logical boundary, like you might have with, say, Java, or it might actually be a physical, quote, physical boundary, which is protected by the hardware, where you have things running in separate processes. But whatever the case is, you can't get to something directly. And of course, Android provides this binder RPC mechanism, which we can use to communicate across the backplane of the device to talk between processes that are always on the same device, but in different address spaces. Another part of the context here is that as you start to develop your system over time, it's often the case that you change your mind about where you want your objects to live. Now, this is really easy to motivate when we start talking about a distributed system. In a distributed system where you've got networks involved, you might start out with things perhaps co-located in the same address space or on the same machine for various reasons. Simplicity of programming is the most obvious one. And then as your customers start to scale up or scale out, you want to add more and more and more processing to your solution. So rather than putting everything together in one address space or in one machine, now you've got multiple machines. And so in that case, you may start changing where things reside over time as your system has to grow, or as you do profiling to learn where the hotspots are, where it slows down, and so on and so forth. But the point is that things are going to change over time. So what are the problems? Well, one problem is that manually writing code to marshal and demarshal communication between address spaces is very tedious, error-prone, and just non-portable. It's just a real pain. Nobody wants to write that code. It's hard to maintain. It's hard to optimize. So you'd really like not to have to do that yourself. The second problem is if you were able to rewrite a lot of code every time they read, configure, and redeploy their software to break things up into different partitioning boundaries, that's a lot of work. And if you program with lower-level IPC mechanisms like sockets, for example, the amount of work required to change from communicating between things in the same address space to things on the same machine in different processes to different processes on different machines, it's a lot of work to do that by hand. And so most people just give up very quickly. They say, the heck with it. It's good enough. I'm not going to worry about it. So these are the kinds of impediments that we run into when we start trying to build systems that have to be broken up across different address boundaries. So what's the solution? Well, as you'll see, there's a multi-part solution here. But one piece of the solution is to define something called a proxy. And the proxy essentially acts as a surrogate or an ambassador that gives a particular interface, actually the same interface, to the client, and then allows the implementation of that interface to be someplace else. And that someplace else could be in a different address space on the same machine. It might be in the operating system kernel being accessed by an application running in user level. It might be another process on another machine. We don't really know. We don't really care. All we know is that the proxy is allowing us to abstract and encapsulate the details of where things actually reside. And that'll allow us a lot more flexibility to move things around. So here's how you might do this on Android. You might go ahead and inherit a remote object from a binder, as we've been talking about many times. And this binder then allows you to be able to export that object to the receiver side. Of course, the way in which you get a proxy to this thing is to describe the interface to this via an AIDL file, which says what the methods are and their signatures and so on. And then you run that through the compiler. You get the proxy, which is generated automatically for you. And then when a client invokes a method call on the proxy, it thinks it's accessing something that's local. It says, service.download image or download file or whatever. It looks like it's making a local call when in fact it's actually calling something elsewhere. Now, where that thing resides, you can control in Android by changing various directives in the manifest file. So you can control whether or not the thing is in the same address space or whether it's going to be in a different address space. You get some control over that. But the point is that whether it's in the same or different, the proxy is shielding you from what's actually taking place. Now, as we'll see later, the proxy pattern is going to work together with the Android binder RPC mechanism in order to implement the broker pattern. And we're not going to talk about that quite yet. That's going to come next. But be aware that that's kind of where we're headed on this thing, is to talk about brokers. The proxy is just a piece of that. If we were thinking about this in broader pattern concepts, we would say that the broker was a pattern language and the proxy was a piece of that pattern language. And we'll perhaps talk about that later. Okay, so as always, these are not just random assortments of classes thrown together for ad hoc reasons. They fit in some grander scheme. This grander scheme has been around for quite a long time. Some of the early work in this area goes back to the early 1980s, so it's been 30 plus years at this point for a lot of this stuff. It's been around for a while. And the pattern is called the broker pattern, and the pattern is called the proxy pattern. And the intent of this pattern is to be able to provide a surrogate or placeholder for an object to allow another object to access it and control access to it. You can take a look here for more information about the proxy pattern. There's a couple different reasons why you would use this. The typical reason why you would use this pattern is if you need to be able to access an object using something that's more powerful than a simple pointer or a simple reference. Pointers and references that you find in C++ and Java are great when you're talking to objects that are in the same address space. When you start having objects that reside in other address spaces, they don't work so great because they can't reach across those address spaces. So that's when we need to have proxies. Another motivation here is to make it easy to be able to change where the objects reside, local versus remote, or co-located versus remote, without changing the way that you access them. So those are the considerations that might help you. Another thing you might want to do here is if you want to have some kind of strong type checking. Let me add that one just for fun. Let's say if there's, let's see, when there's a benefit from having strong, statically typed method invocations. And what I'm really talking about here, what I'm really comparing and contrasting with, is the approaches that use proxies from other approaches that are based on more message passing. We'll talk about those later. Here's a quick synopsis of the structure and participants in this pattern. It's pretty straightforward. This is the diagram from the Gang of Four book. We have a subject, which is really the thing that's defining an interface. Obviously in Android, that's the thing that's defined with AIDL. We have the proxy, which is the guy that is shown to the client, which does the magic under the hood we'll talk about in a second to get the method turned into something that can go over to the receiver side, to the real object, the real subject. And in Android, that's of course handled by the generated code that's stub.proxy, nested inside the stub class. And then finally, we have the, quote, real subject. And in this case, the real subject would be some combination of stub and the actual implementation in the context of Android. When you start looking at this in a distributed systems lens or through a distributed systems lens, you'll see that the Gang of Four description of this pattern is a little bit meager. And there's other steps going on here to get to the other side and turn it back into a method call. But for the purposes of our discussion right now, just think of proxy being the local surrogate or local placeholder or local ambassador to some object that may reside someplace else. And when you invoke an operation on the proxy, it does stuff and then it forwards the call onto the real subject to do the work. This set of dynamics diagrams kind of illustrates this point in a little bit more detail. So the client starts out by getting a proxy from someplace, typically from a factory of some kind, a factory method. Once it's got the proxy, it then invokes a method call on it. As you can see here, most of the time you're using proxies to go across address space boundaries. Not always, but mostly. And so what's happening in this case is that the proxy is turning around and converting the method call that was invoked on it into some kind of message, stripping out or taking the bytes that are coming in as parameters and turning, or the objects that are coming in as parameters, and serializing them into linear byte sequences with a particular encoding format. And then somehow, and this is the part that's not talked about by the proxy pattern, it's getting it over to the real subject to do the work. And when the real subject is done, the call returns, typically synchronously, although you can have variants that do asynchronous interactions. And then it takes the results back, which are in a message format, turns them back into whatever native format is responsible and expected by the caller, and then returns back to the caller. And so either through return value or out parameters or in-out parameters or something, the results are updated and the client gets the results back from the server. So it's basically method to message back to method again. That's kind of the way it works. OK, any questions about the steps, either static or dynamic? So there's a number of interesting consequences of applying this pattern. One of the key ones, and why it gets used so much in distributed systems, is it allows you to, at least in theory, decouple the location of an object from the access to that object. So you can change where the object resides without changing other things. You don't have to change the interface. You don't have a lot of extra work to do on your behalf as a client application developer or as a server application developer. You could also use it to simplify tedious and error-prone details. This is just a little snippet of the code that you would see if you were to peek inside of the download image proxy that's generated for you. And as we've looked at this before, it's kind of messy and ugly, and nobody in their right mind wants to write that code and maintain it by hand. It's just awkward. So we'd much rather have it be done for you by the proxy writer. There are also some potential overheads, however. There's some potential liabilities or downsides with this, one of which is you are at the mercy of the writer of the proxy generator. If the writer of the proxy generator does a good job, then you're in pretty good shape. It's probably equivalent to what you could do by hand. If the writer of the generator of the proxy code does a bad job, you've got lots and lots of overhead, and there's not a whole lot you can do about it unless your middleware gives you the ability to handcraft your own proxies and plug them in place of the ones that are automatically generated. So this is one of those topics that has gone back and forth for decades. There was a time when interface generators were really bad, and so people did a lot of work on optimizing things either by hand or by writing better generators. Just like with everything else, over time people get smarter about this stuff, and so a well-written generator should be competitive to code you would write by hand. In fact, there was some interesting work done maybe, 15 years ago or so by some folks at University of Utah on a technique called Flick, which was an IDL compiler that was heavily optimized to generate code that would be very fast. And it used programming language transformation and optimization techniques to analyze the code that needed to be generated and come up with optimized ways of generating the proxy code. Interesting stuff. Another potential downside, and this really comes back to the issue I added to the slides a second ago, having to do with strong typing. One of the other potential concerns with proxy is it will overly restrict the type system that you have available on the client side. Now this is a sort of a subtle point, and I want to have some discussion about it to see what other people's insights and impressions are about this. So when you start using proxies, you're really saying ahead of time, these are the valid types that can be passed to methods with a particular signature. And here are the results that can come back. You're tightly coupling those things. Now, when you write normal Java code, you write normal C++ code, you do that all the time. So that's not really an unusual thing to do at one level. But when you start moving into a distributed environment, or an environment where you're separating out client and server so that multiple clients are accessing a common shared server, all of a sudden things get more interesting. And there was a fair amount of backlash a number of years ago against strongly and statically typed proxies in middleware for distributed computing systems. And the alternative approach, which you see, by the way, all the time in things like SOAP and other message-based or message-oriented messaging systems, XML-based messaging systems, is stuff where it's more dynamically typed, where you actually create a message, you build up a message piece by piece, usually using some kind of internal coding where you keep track of the type tag, like a tag in XML along with the data. So they're self-describing messages. And you end up, instead of having an interface with lots of different methods with very strongly typed signatures, instead you have one interface called send that takes a message. And the message can be done in some arbitrary self-describing way. So in fact, if you take a look at the messengers in Android, that's kind of the way it is, right? You create a messenger, and it's got a send method. It takes a message, and you put bundles into the message to put anything you want into there. So does anybody want to hazard an opinion about the trade-offs and pros and cons between the proxy-like approach, which is more statically typed, and the message-based approach, which is more dynamically typed? Why would you choose one versus the other? What are the pros and cons?
I like the static typing because you get most of your errors up front from the compiler.
So when you use a statically typed approach, you're letting the compiler and the other tools in the language processing tool chain determine early on when you have inconsistencies between the types that you're creating on the client side and the things that you're passing over to the server side. So strong typing, removing errors. Another thing that comes along with that is often optimization. The more type information is available, usually the more you can optimize things. With strong typing, you often don't have to send over the type information. You can basically have the sender and receiver agree ahead of time. And so the type information isn't sent with a message. Only the data is sent with a message. So the amount of data that's used on the network goes down, and the amount of data to be processed goes down, and so on. So those are arguments in favor of the strongly typed approach. But there's another point of view. I'll never forget when I first started programming back in the mid-'80s, I was reading about Fortran programmers and C programmers who didn't like Pascal. And they would always say, strong typing is for weak minds. So what's the downside with the proxy-based approach, with the stronger typing?
It's less flexible.
Less flexible. And so what that really means in this context is, as your services evolve over time, if you have strong typing, then as your service evolves, all the clients that rely on that service have to also be evolved to take advantage or to utilize the new type information. And so as a result, it becomes, quote, inflexible, because now you've got to go out somehow and change all the clients. And there could be a lot of clients, and a lot of those clients you may not have any control over because they're belonging to some other organization, some other development team, some external group you have no knowledge of whatsoever. So in those environments, especially if you're trying to do things like large-scale enterprise system integration, it's often useful to have a model where you keep the messages dynamically typed. So as you evolve your services, then you can simply have your new clients do new things, add new parts to the message, and when they send it to the service will say, aha, I got a message from a new client, I know how to process that. But the old messages from the old clients will still be handled without requiring changes to the clients. So there's a lot of issues there about trade-offs between forcing changes to the edge of the system, which is what you need to do if you have stronger typing through proxies, versus having the typing decisions done by the service, which gives you more flexibility and dynamism, but is typically slower, has more time and space overhead, and also leads to surprises. As Christoph was just saying, you often don't really realize until the system is running that people are sending you gobbledygook that makes no sense at all. So there's all these interesting trade-offs. So that's a key thing to remember, and probably a good quiz question. What are the trade-offs between the strong typing and dynamic typing in the context of proxy? We'll see. We might or might not see later. There's some use of this in Android, but it's not big enough to maybe warrant it as a full-blown pattern. There's a pattern called extension interface, which is widely used in Microsoft COM and in some parts of Enterprise Java Beans, where you basically have these things called components. And a component is basically an object on steroids that exposes multiple interfaces. And each of those interfaces exposed by the component are strongly typed, and they have proxies. And what you do is you have this little kind of 20 questions negotiation take place between the client and the component, where the client goes out and it queries the component and says, do you support this interface? Oh, you don't? Okay. Do you support this interface? Ah, you do. Okay, thank you. And so it takes what it gets back, and then it makes method calls. So the so-called extension interface is kind of this hybridization between static typing that you get with Proxy and more flexibility that you get with messaging. So it kind of gives you the best of both worlds, or the worst of both worlds, depending on how you look at it. Another problem you have with Proxy is the fact that it's very difficult to entirely shield the application client from the fact that there's a boundary between sender and receiver. So you might like to pretend as though it's invisible, but invariably it's not. And when things go wrong, there are errors that occur when you start running things in different address spaces that do not occur if things are co-located in the same address space. If you make a method call on an object in the same address space, network unreachable is unlikely to occur, right? Whereas if you're running in something that's going across the internet, then someone might cut the network cable with a backhoe or something like that, or the storm might blow down a wireless tower and you lose connectivity or whatever, right? So these are things that you have to be prepared for when you start programming clients using proxies that you wouldn't have to be prepared for if you were just making normal calls. There's a number of known uses here. Most of these known uses are actually much more interesting in the context of the broker pattern, but they also use proxies, so I'm just mentioning them here. We'll talk about it later. The Sun RPC, or the so-called Open Network Computing RPC, remote procedure call model, which started back in the middle 80s, which was a successor to something that came out of Xerox PARC on remote procedure calls by Andrew Burrell and Bruce Nelson. There's also the distributed computing environment, DCE, which came around the late 80s, which was kind of the end of the line of very convoluted, complicated C-based RPC mechanisms. What came next was the combination of the peanut butter of distribution with the chocolate of objects to form distributed object computing, and you get things like Sun Remote Method Invocation, or Microsoft's DCOM, or the Common Object Request Broker architecture, various kinds of object request brokers in this context, Corebout and so on. A lot of stuff done there. They all use proxies very heavily. And then nowadays, now we're 20, 30 years down the road, this stuff resurfaces again, but this time in the context of communication between processes using the binder mechanisms for local interprocess communication on the same device in Android. And it's worth also noticing, if you click on this link here, you'll be taken to a little stub that describes where the Android binder framework came from. It actually came from an earlier work done by BOS, and I think maybe even Palm OS, by a group of people led by Diane Hackborn, who's got the coolest name of programmers in the world. Born to hack, right? We actually have a guy in ISIS called Doug Hackworth, so he's a worthy hacker, I guess. And so they basically wrote this binder, and then they got bought, or they could join the Android development team at some point later, and that's what the Android binder is based on. It's called something called the Open Binder. As I wrap up this section, and then we'll migrate to the next topic, I want to make some interesting observations about proxies. So proxies are a great microcosm of a trend that's been going on in computing for decades, ever since the very beginning of time. And that trend is that useful patterns evolve over time into features provided and supported automatically by various kinds of language processing tools, either programming languages or by tools like AIDL compilers. Here are some examples. If you go back far enough in time, you'll see that the early developers of assembly code were using certain patterns of writing assembly code, and those were things that later found their way into the second generation languages like Fortran and C, where they had things like closed subroutines, or if-else statements, or switch statements, or loops of various kinds of things. Those things all started out by assembly language programmers saying, gosh, if we organize our assembly code in these patterns, it'll be easier for us to maintain. And smart people like John Bacchus, who invented the first Fortran compiler, said, we can actually automate that. We can build a tool that does that for us. It's kind of funny, if you go back in the early days of compilation and second generation languages, there was all kinds of controversy between the super duper assembly language programmers who knew how to write really tight assembly code and do register allocation by hand, and all these newfangled developers who were trying to write compilers to automate that stuff. And there was a lot of controversy. People said, you'll never be able to write a compiler that can generate code better than I can write in assembly, and so on and so forth, which always amazes me and amuses me to no end. Whenever new technology comes along that's threatening to the status quo, people always start out by downplaying its relevance, and then later on they go, oh, well, maybe it solves a few problems, but it doesn't solve all the problems. And then at some point they've been completely overwhelmed and overtaken, and you don't even think twice. You just do it without even stop to think about it. By the way, that meta pattern or mega pattern is described very nicely in a series of books by Clayton Christensen, who writes about the innovator's dilemma and the so-called disruptive technologies that come along. I won't go into it in detail right now, but it's worth looking into because it's great stuff. So the point there is that what was once patterns then find their way into language features. Another set of examples, if you go back to so what I just described was from like the early 60s. You go into the early 70s, there were still a lot of people writing code in assembly language, a lot of people writing code in C at that time, and they were beginning to write bigger systems. And they had to figure out some way of hiding information so that their application developers, which were usually themselves, because the programs weren't all that big, they wouldn't end up making tight coupling on implementation details that were likely to change over time. So if you recall, when we do 251, we talk about stacks. And we talk about different ways of hiding the representation of the stack to avoid writing code that relies on a particular implementation. So what happened there is people began to come up with patterns for hiding information. So like in C, you make stuff static, or you define a header file with a bunch of functions and so on. And what grew out of that information hiding approach, the patterns of information hiding, really turned into the language features for things like classes, packages, and other ways of being able to automatically and through automation and through automatic checking and language tools, be able to make sure that things really do stay private. You can't access stuff. You can make access control checks to keep things from happening. When C++ first started out, and for actually at least a decade or so after it started out, it didn't have any support for parameterized types, which was uncomfortable and inconvenient. Java was the same way for a long time, by the way. So back in those days, people would follow patterns of preprocessor directives or writing little tools with sed and awk and so on in order to annotate their code with template-like syntax that would then be preprocessed and turned into actual code. That experience with macros and these other tools led to people writing templates and adding them to C++ as a template feature. There's lots and lots and lots more examples. So people doing things like the iterator pattern that we learn in 251, and we've talked about here a little bit. The iterator pattern is something that used to be done by convention. Nowadays, you take a look at Java, you take a look at C++11, they've baked the iterator pattern into the language with things like range-based for loops or the for each loop in Java and so on. So once again, you see this never-ending trend towards moving stuff from convention into automation. And there's pros and cons with that, of course. OK, any questions about any of that stuff? So what I'll do next is talk about how the proxy pattern is applied in Android. Some of this is recap, so I'll go through it quickly. I just wanted to put it here for completeness, but I won't spend time on it. So in Android, they basically implement this by automatically generated code. And here are some of the implementation considerations you have to think about when you're using proxies. So one is, are the proxies automatically generated, like a robotic assembly line, or are they something that's handcrafted? And they're trade-offs. For the most part, people rely on auto-generation now. Another question is, you can potentially use a proxy to cache certain information that is stable or immutable, things that don't change. Idempotent, as they sometimes say, where you get the same result if you call an operation multiple times. And you can actually have the proxy cache that information locally so that when you need it, it's right there. You don't actually have to make a remote call to the other side. I kind of think of, anytime I think of caching, I think of hamburgers at a fast food restaurant in a heat lamp, right? So when someone comes in and says, I want, a Big Mac, you don't have to cook one. You just reach back to the heat lamp in the cache and say, here, there it is. It's right there. There's no need to go back and talk to the cook. You've got it in the cache. So for things that are stable, things that occur frequently, things that are worth being pre-cooked, then a proxy can give you access to that. Another implementation consideration, some languages give you some pretty cool support built into the language for proxies. C++, for example, has this interesting feature called the delegation operator, or operator arrow, sometimes called the smart pointer operator. And basically what you can do with this operator is you can use it in such a way where you can invoke something through a proxy using operator arrow that looks like it's actually making a method call. But in fact, what the operator arrow is doing is it's basically intercepting the original call, doing something else, and then returning a result. And then the compiler generates code to redelegate that call to the object returned by the proxy. And there's lots of cool use cases of this. It's used in thread-specific storage. It can be used by a variety of other techniques for being able to make proxies look like pointer access, thereby hiding the details from the application developers. So let's take a look at how you might implement this particular pattern in the context of Android. So this is an Android example using Java. We've seen this already, so I won't spend a lot of time on it. So you run your IDL compiler on your IDL interface, and you get stubs and proxies. The stub is basically the thing that you're going to inherit from and fill in the details to implement later through extension, through subclassing. There's a bunch of helper methods that a stub has, things that are used to register the stub object or the binder object with the underlying binder framework. There's also something that can be used as a method to convert a binder object into a proxy. So that's, you get a proxy back when you call that. The proxy is something that's also automatically generated, and you can use this in order to be able to indicate who the binder is that you want to talk to, the binder object you want to talk to, and also has the code that marshals and demarshals the parameters and sends them across the other side. The other side, of course, ends up being a callback on a method called onTransact, and that's the guy that does the inverse operation from the proxy. That's the guy that pulls all the various pieces out of the message, turns it back into strongly typed data types, and then passes them as an upcall to the implementation method that you define in your subclass of the stub class. So we've talked about that stuff before, so I went through that quickly. So in a nutshell, Android defines the proxy pattern, and it implements the proxy pattern using its generated proxies. It allows you to do various kinds of remote method invocation using the broker mechanism we're going to talk about later. By using this mechanism, there's no API difference between talking to something local and talking to something remote. There may actually be a semantic difference because, for example, if you're talking to an object that's co-located, it's going to end up running in the same thread as the caller. Whereas if you're talking to an object that's running remotely in another process, that will be running in a different address space, and that will be running in a different thread. So there's some different semantic differences to some extent in terms of where things run. But from an API perspective, they look the same. Yes?
So when you're writing a proxy, do you assume that you know where that resource is that you're going to be interacting with? Like, do you write a proxy such that it's going to always be communicating with like a remote, like off? You know what I'm
Yep,
saying?
great question. So the question basically is, does whoever create the proxy, which could be a person or a generator, right? Whoever makes the proxy, what assumptions should they make about where the target object actually resides? And it turns out that there's two answers to that question. The naive approach just always makes things go through the proxy, even if you end up being co-located in the same address space. And I should say naive approach and/or the approach that wants to have semantic consistency of behavior even when co-location occurs. So that's, in that case, you don't differentiate. The optimized approach, which potentially is more intelligent but may also be semantically different with respect to what thread context you run in that case, what the proxy typically does is it takes a look when the call is made and it asks the question, is this object, the target object, in my address space or not? If it's not in the same address space, then it goes ahead and does all the normal things and sends it on its merry way using a broker. If it is in the same address space, it does a short circuit and it goes ahead and just makes a direct call. So you can imagine that that would be way faster than doing all this other overhead. But it also requires, a little bit more checking to take place. Yeah, that's a great question. And of course, the other benefit you get with proxies are that you can make some changes in the way in which you've configured and deployed your system, how you partition your system up into pieces and strewn them around through the processes in the system. without really changing the way in which things are designed and implemented. So what you're doing is you're deferring until deployment time where things reside, as opposed to having to prematurely commit yourself to one deployment over another. And that's another potential great flexibility if you want to build systems that can be sort of auto-scaled without making radical changes to the underlying implementation. Okay, questions about that? So we have one more pattern here. I think we can probably cover this first part of this pattern in the next 15 minutes or so. And that'll leave for us for next time the second half of this pattern. We'll talk about the implementation artifacts of this pattern, and we'll also talk about a couple more patterns. And then we'll get ready to move on to something new. So what we're going to do now is we're going to kind of take the proxy and stretch it out a little bit and put something in the middle, and that something is called the broker. The broker pattern is a pattern that appeared in the Poster 1 book, and then it's been revised various times along the way because the original description needed to be enhanced as people got better insight about what brokers really were. And so we learned a lot about what brokers were over the years. So the context for this is some kind of system with multiple objects that are potentially remote. They may be remote, they may not be remote. And these objects have to interact with each other synchronously or asynchronously. And in the case of Android, of course, this would be over binder RPC. The problems here is we don't want application developers to have to think about a number of accidental and inherent complexities. We'd like them to not have to worry about these details to the extent possible. We don't want them to have to think about low-level message passing, in other words, taking their native data types and manually encoding them, linearizing them, doing all the things that proxies do. They shouldn't have to worry about that. That's basically what Proxy does, by the way. But there's some other things we'd like them not to worry about either. We'd like them to have to not worry about various types of diversity or heterogeneity that pop up in the underlying infrastructure. They shouldn't have to worry that the client side and the server side are written in different programming languages, Java versus C++ versus Prolog versus C. We shouldn't require them to worry about what operating systems these platforms or these applications, clients and servers are running on. They shouldn't have to worry about the networking protocols, the type of the hardware, and so on. That should all be shielded and encapsulated from application level concern. We'd also like to try to shield them as much as possible from other more inherent complexities, things like partial failure, security implications, maybe latency, other kinds of things that may be issues in a system that's getting bigger. We'd like to try to shield them as much as possible. You can't always shield people from these things. If the network gets cut by a backhoe, you may just have an outage, right? It just may not be a way to get around it. But often there's ways of taking alternative paths or being able to have replicas or redundancy or so on built into the system. And it shouldn't be the application developer's job to think about this. I've written a lot of stuff about this topic over the years, and you can take a look. There's many, many sources of information on my website about it. So what's the solution? The solution is to basically separate out the communication concerns that are sort of in the infrastructure from the application concerns and use a broker in order to kind of mediate between those two realms, the systems, the infrastructure kind of stuff, and the application kind of stuff. Now, how is that done in Android? Well, you probably know by now it's done using the binder and the AIDL mechanism. So we implement a binder object that the clients can't get to directly. We get a proxy back to that via the various means we've talked about using on-service connected and so on. And that client proxy is then used by clients, like activities, to invoke operations. And those operations then travel through the system after first being converted into parcels by the underlying proxy. And they travel through the binder framework and pop out the other side to the stub, where they're converted back into data types and passed to an upcall. And that upcall is what actually does the real work to do the logic that's defined by the service binder implementer developer, and then they can pass the results back if it's a two-way call. So the key thing here is that the binder is combining a bunch of things. It's combining proxy, it's combining broker, it's combining activator, it's combining adapter. There's about 8 different patterns. We're just talking about broker. As we'll see later, broker is actually a pattern language. There's a bunch of other things that come along with it for the ride. So the intent of the broker pattern is to try to connect clients with remote objects in a way that allows the broker to mediate the interactions with the clients to the remote objects without requiring the client or server developer, application developers or service developers, to have to know anything about how this works underneath the hood. So you would typically end up applying this pattern if you want to be able to support local or remote communication in a consistent way. You want to be able to make the handling of various fault issues shielded from the application developer. You want to shield the application developer from things like memory management, connection management, data transfer, synchronization, concurrency control, so on and so forth. I should probably list some of these things out. Low-level system details, such as memory management, data, let's see, connection management, synchronization, and threading. You know, you think about it, there's a whole pile of things that you've got to think about if you write all these pieces of code, and you'd like that to all be hidden from you as much as possible. Different implementations of brokers, by the way, go to different extents to hide you from some of these things. So here's basically the structure of this pattern, and I'm pulling this particular structure from a couple different places. I wasn't really happy with any one description of this stuff from the literature out there. So here's one I kind of came up with based on a few things. So basically you have a client, which is like an activity in Android, the guy making the call. You have some kind of infrastructure, like the Binder RPC framework, which is broken up into requesters that send things and dispatchers that receive them and process them and upcall them. You then have demarshallers, demarshalling and marshalling, and they do the serialization and deserialization. That's what we typically think of as being the proxy. And then you finally have the guy that does the real work, which is called a servant in this particular context. Sometimes people call these things executors, but we'll call them servants for now. So those are the main components that you would typically find in a broker. And if you take a look at this paper, it gives you a flavor of this. It uses slightly different names, but it's the basic idea. Here's a picture that kind of illustrates how all this stuff works. A server registers an object either through some kind of configuration script, like a manifest file, or dynamically through some kind of API. It says, you know, here's an object that needs to be accessed remotely. That's what the starts out, so that everybody knows that exists. Then a client is going to get back an object reference or some kind of service identifier to this object, and it's going to go ahead and invoke an operation on it via a proxy. And it'll call this on the requester. The requester will set up a connection if it doesn't exist already, do the marshalling, send the data over. The data goes over via the broker. The broker might or might not be a separate process or a separate thread. These might be libraries that are linked together. It might be some intermediate mediator that is separate from the client process and the receiver process. Really depends on a lot of different things. Scalability, fault tolerance, memory utilization, battery power, all kinds of different considerations come into play. The dispatcher takes the request, basically works with the demarshaller part to crack open the data, extract out the message fields, turn them into data types, and then make an upcall back to the object. The object does its work, the method on the object does its work, and then it sends the response back, which goes back by the inverse path of how it got there in the first place, most typically. So those are essentially the dynamic steps with the broker. This obviously maps very nicely onto what's going on in the context of Android for a whole bunch of different reasons. And we'll talk about those next time when we talk about implementing this pattern in the context of Android. We'll look at the steps and the interactions. There's a whole bunch of different consequences of using this particular pattern. A bunch of good things. Location independence. You don't really know or care where the objects reside. They might be in your address space. They might be someplace else, as Nolan was talking about. So that gives you more flexibility. There's a clear separation of concerns. The infrastructure, the broker implementations, doing all this heavy lifting for you, so you don't have to worry about it in your application, unless there's a bug in the broker, but that's another story. And if you make changes to the implementations, the clients typically shouldn't be affected by that. And then there's also a whole pot of other benefits. If you implement brokers using standards, like Corba, for example, or other technologies in that space, like SOAP and so on, then what you'll end up with are ways of being able to get portability. You'll be able to get modularity. You get portability because you'll have common interfaces that are standardized through open specifications. You will get modularity because you can break your system up into pieces and you can test them individually. You get reusability because you can reuse both the broker infrastructure as well as services you build on top of it and objects you build on top of it. And all of this stuff has many, many, many patterns galore to make it all work. There are some downsides. For many years, especially in performance-critical environments, environments where the right answer delivered too late becomes the wrong answer, those kinds of mission-critical or safety-critical environments, people had a perception that brokers added too much overhead relative to hand-coded solutions. That has changed over the years. People have gotten really good at implementing very high-performance brokers, but sometimes if you're in certain environments, there may be too much overhead. Potential issues with reliability. Reliability is something that's often very hard to define in a completely generic and common way, because different applications have different reliability needs that are often not well served by a one-size-fits-all solution. So if you're not careful, you might end up compromising your reliability requirements to use something that's defined off the shelf by a broker, and it might not work as well as something you might handcraft yourself. Having said that, it takes a lot of work to handcraft these things yourself. And of course, anytime you start having layers of stuff involved and many different components, you quickly realize you've got a big issue as far as debugging and testing. The minute you've got distributed anything or concurrent anything, there's a lot more stuff running around. And you've probably already seen that as you're trying to debug your programs here. If something goes wrong, is it because the service didn't work right? Is it because the client didn't work right? Is God help us if Android's not working right? That might happen once in a blue moon. But you just have to be very thoughtful about where things are going wrong. There's a number of known uses of broker. Once again, the early days were sort of procedure call-based brokers, DCE, ONC, or Sun RPC. Corba, probably the predominant example of a broker. Corba is so much a broker. Broker is its middle name. It's the Common Object Request Broker architecture. It's right there in the name. And then, of course, nowadays we get Android. I want to talk briefly about this whole issue of manually doing things versus automatically doing things. And as I kind of alluded to before, there's always this paradigm shift that occurs in any domain, any field, as things that used to require human expertise are gradually overtaken by automation. I was just reading the other day that apparently it used to be the case a couple years ago that humans aided by computers could beat computers at chess. And now it's apparently no longer the case. Computers are so good at playing chess that you don't need humans to help them play a better job than a human playing with a computer can do. So I thought that was interesting. One more thing humans aren't good at, right, compared to machines. I would argue there's an awful lot of things humans aren't as good at machines at, but there was a time when they were. And whenever people tell me those things, and by the way, as you go through your technology career, you will see the following meme pop up over and over again as new stuff comes along. Because at first, it won't be that good, and people will poo-poo it, and over time, it'll get better and better and better. So my favorite example of this phenomena, which is really at the heart of the innovator's dilemma that Clayton Christensen liked to talk about, is the famous story of John Henry. Does anybody remember who John Henry was? What was John Henry's great feat?
He laid on railroad.
He was a railroad worker, and his great thing was he's a real big, strong guy, and he could take a sledgehammer or an axe, and he could sort of single-handedly chisel through massive amounts of rock to make railroad tunnels. And so there's a great story where John Henry goes out and he competes against a steam drill. And in those days, the technology wasn't very good. And so, they have this contest. The day starts, the steam drill starts drilling, and John Henry starts, chopping away with his sledgehammer. And the steam drill keeps, breaking down, and they have an army of technicians running around trying to fix it. Sounds a lot like software sometimes. And so what happens? Does anybody know what happens in the story? Who wins? John Henry wins, right? He gets through that mountain first. But what happens to John Henry? He dies, right? So there's a metaphor there that says through superhuman effort, you can sometimes beat the machine at certain points. But it's often not worth it, right? You may pay a big price for doing that. So the real thing to do, of course, is not to try to beat machines. It's to write better machines, right? That's how you make it big. Be wealthy, popular, and famous. Okay, so that's it for the lecture for today. What we'll do next time is finish off broker implementation, and then we're also going to talk about observer, because that's sort of the last, I think that's maybe the last big pattern that we've been talking about in all this stuff. And then we'll get ready to start talking about content providers.